Zero. I don't make relax rates. So usually linear equations are ugly. The coefficients are like that and the solution are ugly. When you want to eliminate things, it goes wrong. With determinants, it's much easier. In this case, we are calculating D. That's a determinant 5, 3, 27, minus 21. And this is minus 105, minus 81. So together it's minus 186. Then we calculate the determinant of x. That will be 527, 321, 83, 49. Remove that column. We are left only with 3 minus 21, 83, 49. So 3 times 49, 147 plus 21 times 83. I don't want to compute that. Next one is 5, 27, 83, 49. This one is 245. 245 minus. Well, again.
2,200. I mean 21.
2,221.
And up is 2,384.
2,384. 2,000. Okay, don't count. That's not that important. So now, having this, we can immediately write the solution that x is equal dx over d, and this thing is going to be 147 plus 21 times 83 divided by minus 186. Y is going to be 245 minus 27 times 83 divided by minus 186. These are some numbers, ugly numbers. But my point is that all the solution is very clean. It's very difficult to make mistake with these Cramer's formulas. So every time I have to solve linear equation on paper, I'm using this type of formulas, not to make any mistakes. Good. Now we come back to our problem. From this level. We have four situations. First, this situation determinant is non-vanishing. Then we use Cramer's formulas. That's the situation number one. Now the next thing that we do is this situation. That would be our situation number two. Let us see what happens in this case. Let us take an example of problem, and let's see what we can do about that. So we take that type of situation. If you don't copy something, don't worry, we are recording, so you can always check later. So let us solve the problem in which the matrix A looks like that, the vector X looks like that, and the vector B is the short one. For example, I prepared here a problem, let me just copy this. 3x plus 4y minus z plus 2w equal 3. X minus y plus 2z minus w equal 1. That system of linear equations can be written as three, 4, minus 1, 2, 1, minus 1, 2, minus 1, x, y, z, w equal 3, 1. That's our matrix A, that's our vector X, and that's our vector B. Clearly, I cannot take the inverse of A. What you do in this situation, the solution is quite easy. You change it in a square problem. How? For example, by choosing 3x plus 4y x minus y and putting the rest of the equations, this one, on the other side. If you do that, then on the other side you get 3 plus z minus 2w, 1 minus 2z plus w. Then this new problem can be rewritten in a matrix form in the following way. 3, 4, 1, minus 1, x, y, three plus z minus 2w, 1 minus 2z plus w. Now, this is our new matrix A, call it A prime. This is our new vector X, call it X prime, and our new vector B, B prime. Now, can we compute inverse of this? That depends on the determinant of this new matrix, and this is minus 3, minus 4, minus 7, different than 0. So yes, this problem has solutions. So what we do, we calculate d, and this d is minus 7. Then we calculate dx, and our dx is determinant of the matrix. We remove 3 and 1. We are left with 4 minus 1, and the other side is 3 plus z minus 2w. 1 minus 2z plus w. dy will be similar, but we remove the way I solve it. So we are removing that one, and in this space we are putting that. So actually this determinant would be equal to 4 minus 1. And this one would be equal to 3, 1, 3 plus z minus 2w, 1 minus 2z plus W. Okay. So now this is minus 3 minus z plus 2w minus 4 plus 8z minus 4w. This one is going to be 3 minus 6z plus 3w minus 3 minus z plus 2w. So in this case we have minus 3 minus 4 is minus 7 z plus 7z 2w minus 2w. In this case, 3 minus 3 is 0. Minus 7z, 3w plus 5w. So from that, we are finding the solution. X equal dx over d minus 7 plus 7z minus 2w divided by minus 7, which is 1 minus z plus 2 over 7w, and y minus 7z plus 5w divided by minus 7, which is z minus 5 over 7w. Let's check if I got the same results. 1 minus z plus 2 7 z minus 5 over 7. Okay, so that's the solution to that problem. We solved this problem, and now we can come back to the original problem X. So I need some more space, so let me remove that thing. That's the original problem. And that's the original solution. So the original solution has the form of x, y, z, w. Now what we found is that x is equal to that. 1 minus z plus 2 over 7 w. Y is equal to that. Z minus 5 over 7 w. Z is just z, and w is just w. That thing could be rewritten in the following way. You could take z-dependent terms and put z in front. Then here you get minus 1. From here is 1. From here is 1. Here there is no z, so 0. You can take w-dependent things and put the w out. Here you get 2 over 7. Here you get minus 5 over 7. Here there is no w, so 0. And here there is w, so 1. On the top of this, there is a vector that doesn't contain z and w at all. So here is 1. Here there is nothing, nothing, and nothing. 0, 0, 0. And that thing is the real solution of the problem that we started with, of that problem. What is the value of z and w? Doesn't matter. For any z and w. How many solutions? Of course, infinitely many solutions. Is this process clear? You start with 2 equations for 4 variables. You choose 2 variables, put it on the other side. You get 2 equations for 2 variables. You solve it. After you solve, you take these old variables x and y, and you replace them by function of z and w. Then your solution is dependent on 2 parameters, z and w. And you express family of solutions by taking something that is independent of z and w, a vector that is proportional to z, and vector that is proportional to w. And now this z and w can be any numbers. I would say z and w are any 2 complex numbers. Then, of course, since there are many different z's and w's that satisfy this, we have infinitely many solutions. Now, you should ask me a question. Why I take z and w to the other side? Why not x and y? And my point is, no difference. You would get slightly different looking solution, but exactly the same, equivalent. It doesn't matter what you put on the other side. What is important, that the new matrix here, A prime, is non-singular. That you can invert. That's the important part. That you can later divide by this. If that would be 0, this D, you would have problems. So important is that the new matrix A prime that you get is non-singular. So usually what I do when I decide what to put on the other side, I have a look. This -3, -4, -7, good. Can I choose X and Z? Let's check. 3 times 2 is 6. And here is plus 1, 7. Also I can do. Can I choose X and W? 3 times minus 1 is minus 3. Minus 2 is minus 5. It's also okay. So you can choose whatever you like. To keep it on the left side and put the rest on the right side. Okay? Very nice. Now we come back . So we had a situation when matrix was square, X and B had the same size, and determinant of this matrix was non-zero. That was the first situation we solved by Cramer's formula. We had the second situation when the matrix A was long and what we did, we cut this part and we put it on the other side. Well, it's difficult to write it in this form, but after doing that, we got a square matrix here, which determinant was non-zero, so we could again use Cramer's formulas for the new problem. Now we go to the third situation, namely that situation. Let's take some example corresponding to that situation. Situation 3. Well, x plus y equal 1, x plus 2y equal 5, x minus y equals 6. That means 1, 1, 1, 2, 1, minus 1, x, y equal 1, 5, 6. Now first, does this system of equation have solutions? And my expert says no. Very good. Why? How do we know? These equations are contradictory. There are few ways of checking that. First way of checking that, what I was teaching you before, my matrix A, 1, 1, 1, 2, 1, minus 1. The largest determinant you can find is determinant 2 by 2. This is 2 minus 1, so the rank of A is 2. Then I form my matrix M. My matrix M is 1, 1, 1, 1, 2 minus 1, and I'm adding that column. 1, 5, 6. Let me check
if that determinant is 0 or non-zero. I have 12 plus 10 minus 1 minus 2 plus 5 minus 6. 22, 27, 20, 18. So the blue determinant is non-zero. This means that the rank of M is 3. Since this is larger than that, no solutions. There are other ways of getting that result. For example, from that, you could subtract minus 1 time, and you can subtract minus 1 time, and this system of equations become x plus y equal 1, y equal 4, and the last one is minus 2y equal 5. Clearly that condition here gives y equal minus 5 over 2, while this condition gives y equal 4. These are contradictory conditions, so no solutions. To do that, you have to solve the problem. Here, we didn't have to solve the problem. We know that there is no solution simply looking at the rank. Which one you prefer? Up to you. So this system has no solutions. So I write here, usually no solution. However, life is never that easy. And when I was studying mathematics, a question they were asking is, if you have 3 points, can you put a line through them? Not always, right? But the answer they gave me is always, depending how thick the line is. And there is something in this. If you make a thick line, it will cover these 3 points that are not on one line. How this is called? I don't know how it's called in English. Adam, you help me. Least square fitting. How do you say in Chinese?
最小平方法。
Least square fitting. So it's a best solution you can get for a contradictory system. So, as I said, usually that system doesn't have solution. It really doesn't. But you can find a solution that is the best. It doesn't satisfy the equation, but it's providing this thick line that is giving you the trend of the points. Sometimes that really makes sense to find such solutions. In other situations, it doesn't make any sense. You can put deadline, 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 all lines are put here. But sometimes it really makes sense to find a solution in that form. So now, how do you find that solution? That's our next thing to be done. So for that particular system, we want to find the best solution called least square solution of that problem. How to proceed? Turns out that the story is quite simple. Let me show you. So I know that there is no real solution, but now I find the solution in the least square sense. How to do that? Again, that's my problem. In order to find x, I would like to change this A into a square matrix. How to change A into a square matrix? How to make it square? Yes. You multiply this equation on the left side by the matrix A transpose. Matrix A transpose looks like that. If you multiply this equation by the matrix A transpose, you are getting the following thing. A transpose times the matrix A times the vector x equal A transpose times the vector B. Now, if you multiply these two matrices together, you get a matrix that is square. This is the matrix A, T, A. X is still the same X. And on this side, you have a vector obtained by this multiplication, and this vector has this side, this size, A, T, B. Now, by doing that, you get a new problem that you can solve. Solution to that problem is easy. X is simply A, T, A inverse multiplied by A, T, B. And that solution is called least square solution. This is all very theoretical, but in a moment we will calculate least square solution to the problem that we have there. You should immediately ask me, but what happens when this matrix is singular? It can happen. If this matrix is singular, then we get here the case 4, when the problem is square, but the determinant of the matrix is 0. And I will discuss this problem in a moment. For now, we just assume this matrix is non-singular. If it's singular, we will come back to that in a moment. Very nice. Everything clear? Now what we do, we find the least square solution to our problem that I wrote here. Here is our problem, and now it's time to find the least square solution to that problem. A is equal to 1, 1, 1, 1, 2 minus 1. B is equal to 1, 5, 6. A transpose is equal to 1, 1, 1, 2, 1, minus 1. Now I have to calculate A, T, A. That's going to be matrix 2 by 2. 1, 1, 1 times 1, 1, 1 is 3. 1, 1, 1 times 1, 2 minus 1 is 2. Correct me if I'm doing something wrong. 1, 2 minus 1 times 1, 1, 1 is 3 minus 1 is 2. And 1, 2, 1 times this is 1 plus 4 plus 1 is 6. A, T times B is a vector 2 by 2, 2 by 1. And it's going to be equal to 1, 1, 1, 1, 5, 6, 5, 6, 12. This times this is 10, 11, minus 6 is 5. So now I arrived at this problem. And this problem is 3, 2, 2, 6, x, y equal 12, 5. Somebody was good at calculating inverses. What's the inverse of that? Let me use the results from today's class. When I did the matrix A, B, C, D, this is equal to 1 over A, D minus B, C. D minus B minus C, A. So what is it in our case? A, D, 18, 14, right? This is 14. B, 6, A, 3, minus 2, minus 2. So that matrix is 6 over 14, minus 2 over 14, minus 2 over 14, 3 over. That's correct? I'm not sure if this is really inverse, we didn't make mistake, but now I see that my solution to the problem, x, y, is that matrix 6 over 14 minus 2 over 14 minus 2 over 14 3 over 14 times the vector 12, 5. Which is 6 times 12, 72, 62, and the bottom, minus 24 plus 15, 9. So finally we are getting 62 over 14 minus 9 over 14. So that's the least square solution to the problem. These are the best values of x and y that are satisfying our equations. Good. We know what to do. When we have a square problem and determinant is different than 0, we use Cramer's formula. When we have a long problem like that, we take part of the variable to the right-hand side. We get a solutions that depend on parameters, usually infinitely many solutions. When we have an overdetermined system of equations like that, usually there is no solution. And if we find there is no solution, the best thing we can do, we can find the solution in the least square sense. Now, it happens sometimes that after we do this matrix A, and we calculate the determinant of this matrix, we can have a case when it's different than 0 or when it's equal to 0. When it's different than 0, then we know, we just did. You get the least square solution. But if you have a case equal 0, then you cannot take the inverse. That's the same situation here, when you have a square matrix with a 0 determinant. Now, I show the last situation. What to do when you have a square problem, but you cannot solve it because the matrix is singular. Then you get something what is called generalized solution. Let me now explain. Let's take a problem x plus y. No, first I want to go to a general theory. You have a problem A, x equal b, that looks like that. A is a square matrix, x is a vector, b is a vector, and you found that your determinant of A is equal to 0. In principle, you would be happy to write your x as A inverse times b, but you cannot do that because this doesn't exist. So the question is what you can do. In this case, inverse doesn't exist, but there exists something else. We call this thing GI, and that stands for generalized inverse. Now let me explain. When matrix A is non-singular, then it has eigendecomposition, and this diagonal matrix of eigenvalues looks like that. If determinant of A is different than 0, that means that lambda 1 is different than 0, lambda 2 is different than 0, all lambdas are different than 0. In this case, inverse looks like H inverse H minus 1, when this diagonal matrix lambda inverse looks like 1 divided by lambda 1, 1 divided by lambda 2, 1 divided by lambda n. This is something that we studied in today's class, and we did exercise. That happens, this is all true when determinant is different than 0. Now, what happens when determinant is 0? Then, one of these eigenvalues is 0. At least one, maybe 2, maybe 3. I don't know, but at least one of the eigenvalues is 0 if determinant is 0. So, coming back to that matrix A with determinant A equals 0 also has eigendecomposition. And this decomposition looks exactly the same, except that this diagonal matrix now has non-zero eigenvalue up to m, and after m, there are zeros on the diagonal. Some of the eigenvalues are 0, we put them at the end. Maybe 1, maybe 2, maybe 10, I don't know. But at least 1. Now, you cannot calculate inverse of this because of the zeros. But you calculate something what is called generalized inverse. And this generalized inverse look very similar to that thing. It's 1 divided by lambda 1, 1 divided by lambda 2, 1 divided by lambda m, and then it should be 1 over 0, which is infinity. I cannot do that. If I do that, all matrix blows up. So what people did instead? They put 0 all the way to the end. Zeros goes to zeros in the generalized inverse. It's kind of ignoring this segment of the space. And if you put this back in that, then you get the equation for a generalized inverse. This is simply H generalized inverse H minus 1. And now you find solution to your problem. X is A generalized inverse times B. Again, the solution doesn't exist, but the best thing you can do is find this generalized solution. Which looks like that. I think that's a good time for another play. you have any questions, you are welcome.